In this section, we're going to look at some different word problems. So dealing with quadratic functions, as well as some applications with business models such as supply and demand and profit, revenue, cost, things like that. All right, so this first example here, we have the supply for a certain product can be modeled by P equals 3Q squared. In fact, let me just make a note to myself. So we have supply is coming from P equals 3Q squared, and demand can be modeled by P equals 1,620 minus 2Q squared, where P is the price in dollars, Q is the quantity in thousands of items, and we want to find the equilibrium price and quantity. And again, equilibrium is when supply is equal to demand. So what we're going to do is take these two equations and set them equal to each other. So supply is 3Q squared, and we're going to set that equal to demand, which is 1,620 minus 2Q squared, and we're going to solve for Q. So I'm going to add 2Q squared to both sides. So we'll have 5Q squared equals 1,620. Divide both sides by 5, and that'll be Q squared equals 324. And what we're going to do here is take the square root of both sides. Now, when we take the square root of both sides, typically we have plus or minus for our answer. However, with word problems, typically we're only having positive values come through. But I just like to make a note of that because when we're solving algebraically, like in previous sections here, we would have that plus or minus. But for this, where we're trying to find the quantity of items, we'll just have the positive value of square root of 324 is 18. So we found Q, now we just need to find P, and what we can do to find P is just plug in Q into one of the equations. Supply or demand, doesn't matter which one. I'm going to use the supply equation since it's just a little simpler. So I'm going to go 3 times 18 squared, and that should be 972. So the equilibrium price is $972, and the quantity is 18, but notice the units here, 18 thousands of items. So we're doing 18,000 items. All right, so with that one, they gave us the supply and demand models. They happen to both be quadratic, and in solving, we set the two equations equal to each other. Now let's look at a bit more complicated one. We have a company is planning to sell a new smart fitness device. Developing the product will cost $700,000. And each device will cost $30 to manufacture. So in terms of cost, we have two pieces of information. There's this fixed cost of $700,000. And then there's this variable cost coming from $30 per device. All right. Market research suggests that if they sell the device for $100, they will be able to sell 30,000 items. So I'm just going to highlight that. So if they set the price of $100, they can sell 30,000 items. For each $10 they lower the price, they estimate they will sell 5,000 more items. So in terms of sales here, we're given this relationship of $100 and 30,000 items. Those go together. Then they also tell us this change in change in sales. And what we're going to do here is think about this as slope. So the idea is if they lower the price $10, so it's like if we take away $10 from the price, the quantity is going to increase by 5,000. So with slope is the change in output over change in input. So what we're seeing here is where we're working with these functions that are P of Q, where Q is the input and P is the output. Then for sales, what we're seeing is a relationship with slope where the change in output, so change in price, I can represent this as a fraction. So the change in price in the numerator, our change in output, would be going down $10, so a negative 10. And then the denominator would be increasing by 5,000. So I'd have a positive 5,000 in the denominator. So this ends up giving us a slope. It's just describing it in kind of this fraction form. So this would be a negative 0.002. All right. Oh, and part of that was that we're assuming that quantity demanded is linear related to price. Okay, so we want to determine the price that will maximize profit. So again, with profit comes from taking the revenue minus the total costs. Now with total costs, we're getting a equation here where we have our fixed cost of 700,000 and we're adding on a variable cost of $30 per device. So in terms of cost, we're going to have P equals that fixed cost of 700,000, and then we're going to be adding on $30 per device. So that's going to be 30 times Q. So this is our linear model where it's slope and intercept. Slope is the rate of change. Intercept is that fixed value that we're starting at. So we have this equation for cost. For sales, we need to do a little bit of work. We have the slope, but we don't have the intercept. But we can find the intercept using this information of, it's like we have a coordinate of $100 with, other way around. Quantity is the input, so it'd be 30,000, comma 100 for the coordinate, where 100 is the price. So it's like we have the setup, we have P equals negative 0.002 Q, but then we don't know our intercept. But if I plug in this coordinate, so P equals 100 equals negative 0.002 times 30,000 plus B, and then I can solve for B. So 100 equals, taking care of that multiplication will be in negative 60, and then plus B, add 60 to both sides, so B equals 160. So for sales, what we're going to have is P equals negative 0.002 Q plus 160. Okay, so that's setting so what we have here, let's go with what we have here. This is calculating total cost. Total cost is coming from the 700,000 plus 30Q. What we have for sales here, this is describing the price for sales, which isn't quite done in terms of having our equation for revenue. So remember, for profit, I want to take revenue minus total cost. Well, we have total cost is done. We have that calculation. We have this information for sales, but remember that revenue, so calculating how much money we're actually making, Revenue comes from taking the price times the quantity. So revenue equals P times Q, which for us, we just found that the price for sales is this negative 0.002 Q plus 160. The thing is, we just need to take that price that's coming from sales and multiply it by the quantity so that we can see how much money we're making. So really, revenue is, if I distribute that Q in there, is this negative 0.002 Q squared plus 160 Q. Okay, so revenue just had this one little extra step of taking the quantity times price, where we calculated price based on this information from the sales. Okay, as you can see, I'm squeezing all of this on the left-hand side here because now we can actually do our work. Now that we have those two equations, so to calculate profit, we're taking our revenue equation, which we just found as that negative 0.002 Q squared plus 160Q, minus the total cost, which is the 700,000 plus 30Q. And what we want to do is simplify. So we're calculating, we're getting a function, or sorry, an equation for profit. So we're going to have negative 0.002 Q squared. We're going to have 160Q minus 30Q, so that's plus 130Q. And then minus 700,000. All right, so we get this information out, and what we want to do, so we want to, assuming quantity demanded is linear related to price, determine the price that will maximize profit. So we want this maximum profit, and when we want to maximize or minimize, what we're looking for is a vertex. We're looking for this largest value. And what we have here for profit is a quadratic equation. And especially like a maximum makes sense because our parabola is opening downward. So what I want to do is using this A equals negative 0.002, B equals 130. We don't really need C, but C equals negative 700,000. I want to find the vertex. So X, which in this case is actually Q, Q is going to equal negative B over 2A. So negative 130 over 2 times negative 0.002. So that's going to give us, on my calculator, 32,500. So that's the quantity that maximizes profit. We're interested in the price that maximizes profit. So for price, we have two equations. Maybe that's what I should have done up here, is that really, instead of P, up above here, I'm going to change that. So cost equals the 700,000 plus 30Q. So really, in terms of price, we're using this equation from sales. This P equals negative 0.002Q plus 160. So if I want the price that will maximize the profit, then I want to take negative 0.002 times Q, which we just found would be that 32,500 plus 160. So price, if we plug that in, should be 95. They don't ask for it, but if we wanted to know what the maximum profit would actually be, we would take that 32,500 and plug it into that quadratic, so that negative 0.002Q squared plus 130Q minus 700,000, that would calculate it. But we just want to know the price. So the price that would maximize profit is $95. So let's just run through this scenario again. This company, they have an idea of a fixed cost, like fixed costs that can come from rent and salary and things like that. But then they also know each device will cost $30. So that variable cost may be things like materials and equipment needed and things like that. So altogether, those two pieces make a linear equation that calculate cost. Then in terms of sales, they can see this behavior with price. So when they had the price set at $100, they could sell 30,000 items. Then they saw that if they lowered the price $10, they could sell 5,000 more items. So we got this relationship for how changing the price changed the quantity. So with that, we got a linear equation that described the behavior of price coming from those sales. So since we were interested in profit, we took the revenue, which is that price times quantity. So from sales, we took that equation for price and multiplied it with Q, and then minus the total cost, which was that 700,000 plus 30Q. Then finding that equation for calculating profit, to maximize profit, we're looking for a vertex. So we use that x equals negative b over 2a to solve. Okay, one last example here. We have a ball is thrown upwards from the top of a 40-foot high building at a speed of 80 feet per second. The ball's height above ground can be modeled by the equation h of t equals negative 16t squared plus 80t plus 40. We want to know what is the maximum height of the ball. So again, maximum or minimum, we're thinking vertex. And when does the ball hit the ground? So here we're looking for where h equals 0. So what we're looking for here are like the x-intercepts. In this case, it would be the t-intercepts. So we have those two pieces. So let's start with the maximum height of the ball. And what can help too is thinking of like when we get coordinates out, our input is t, output is h. So we're working with a equals negative 16, b equals positive 80, and c equals 40. So the first part of the question, getting that maximum height, we're going to take the vertex. So t equals negative b, which would be negative 80, over 2 times a, which would be 2 times negative 16. And that should be 2.5. And then what we will want to do is, so that gives us the time, so it's reaching a maximum height after 2.5 seconds. But then what we want to do is take h of 2.5. So plugging in 2.5, so like negative 16 times 2.5 squared, plus 80 times 2.5, plus 40, and just plugging that into a calculator, and that would be 140. So the maximum height of the ball is that 140 feet. Is 140 feet. And we have more information like that it occurs after 2.5 seconds, but they don't really ask for that. Okay, our next piece, when does the ball hit the ground? So we want to see where does h of t equal 0. So we're solving 0 equals negative 16t squared plus 80t plus 40. And what we're going to do here is use the quadratic formula. So we're going t equals, and we're going to have negative b plus or minus square root b squared minus 4ac all over 2a, and then we're just plugging in our values. So negative 80 plus or minus 80 squared minus 4 times negative 16 times 40 all over 2 times negative 16. Okay, so we're going to have negative 80 plus or minus, simplifying that square root is going to be a square root of 8,960 over negative 32. And then what we're going to do is use a calculator to evaluate the 2 scenarios. So we want the one where there's addition and one where there's subtraction. When we use addition, we're going to get a negative 0.458. When we use subtraction, we're getting a positive 5.46. For t to be negative just doesn't make sense here, like having a negative time. So with that, we're going to throw out that answer, and our only answer is going to be that positive 5.46. So the ball hits the ground after 5.46 seconds. So just in terms of a visual of what's going on here, actually, let me draw this. So we're on a 40-foot building, and what we're doing is we're throwing a ball up and out, and then it comes down to the ground. So in terms of the maximum height, so that came from the vertex, so that came from this 2.5, 140. So what we're seeing there is how much time has passed, so 2.5 seconds, and having a height of 140. So we basically threw it 100 feet above the building that we're standing on. And then the ball turns and goes downward and ends up hitting the ground. So that's where we have a height of 0, and what we just found is this 5.46, 0 as a coordinate. So what you can do is kind of looking at those numbers together, that makes sense, like that the vertex happened almost halfway between where we started and where it ended up hitting the ground.